Hi, in today's video we are going to be vibe coding the ChaCha20 Cipher using the C programming language. And by vibe coding, I don't mean that we are going to use LLMs. I mean that we are going to get good vibes, and we are going to read the documentation, and we are going to actually handwrite all the code. And the reason I'm doing another C video after so many Go videos is that yesterday I made a poll on my channel because I'm going to Japan tomorrow and I'm thinking of finally making a travel vlog. So I made this poll. So to that one person who voted that you're going to unsubscribe if I make a travel video, I'm very sorry to see you go, because I think making a travel video is another milestone in my YouTube journey. Is another milestone on my YouTube journey. And there are two people who voted just make more C videos. And I think, actually you are right. I'm going to make a new C video, and this is actually going to be pretty interesting, because this is the ChaCha Cipher, and the ChaCha Cipher is actually used in multiple heavy-duty TLS implementations. So ChaCha20 used with the Poly 1305 AAD, as defined in this RFC 8439. It's a pretty strong cipher, and at the same time it's very easy to implement, and it's very it works very well on low-end devices, because for most of the time it only uses XORs. It uses 32-bit unsigned arithmetics and left binary but bitwise rotation. So all of these operations can be performed very efficiently on even very simple hardware and on 32-bit chips. So if I remember correctly, it was Google who advocated including ChaCha20 Poly 1305 into the TLS standards, and it's one of the cipher suites used in TLS 1.3. And I think, so when you actually click on, okay, so you don't see it here. If you open the network tab, you go to privacy and security, you can see what cipher your TLS connection is using. And this particular website uses AES GCM. This is also a very strong cipher, but it works best with hardware acceleration. So it doesn't really work well on embedded devices or on like smartphones or anything like that, because some of those chips don't have acceleration for AES. And this is running, like this computer I'm recording this on, it's I think it's a 13th generation i7, so obviously it does have AES acceleration, because it's one of the hallmarks of like late i7s. But maybe if we just continue searching, we will find a website that's embedded with ChaCha, right? Nope, AES. And this is AES. Okay, so technically it is included in TLS. It's just not very commonly used on machines with actual support for AES. Yeah, so that was me yapping about this being included in the TLS 1.3 standard. I think it is. Anyway, ChaCha is very simple, and it's also, I think it's actually also pretty secure. And yes, Yes. And anyway, so I think we could start by actually trying to write some code, and then I'm going to slowly so we're going to slowly discuss how it actually works in practice. So what I have here? Okay, ChaCha20 video. CD ChaCha20 video, and I'm going to touch main.c. I'm going to ignore a.out, and okay, I'm just going to write it in a proper gitignore file. So we're going to ignore a.out, we're going to ignore main and main.exe if you are building this on Windows. And then I'm going to initialize a Git repository, add everything in here, and we are going to commit an initial commit. So as mentioned, this is going to be vibe coding. We are going to do it in a very relaxed manner because this is we only care about vibes. We do not care about doing things quickly, right? So in main.c, you know what? Actually, we probably need to write some tests right from the outset. So how did we do it? I need to find some documentation or like a tutorial how to use getting started with CUnit. Writing CUnit tests, okay. Okay, about the test registry. Okay, so I'm going to define our ciphers in a header file. ChaCha20h, define ChaCha20h, and if you're new to C, this is a technique used in many, like in idiomatic C code, to indicate that this file should only be included once. And I think we could. So the first thing we're going to need is we're going to need a quarter round function, and the quarter round function is a basic operation in ChaCha20, and it's basically like a series of these bitwise operations, and they are all operating on 32-bit integers. So we know that we are going to need stdint.h, and we know that we are going to need okay, let's just say ChaCha20 quarter round. Or you could probably shorten it to Q round, because Q round, and we're going to use uint 32ta, uint 32tb, uint 32tc. Oh, and actually all of these need to be pointers because we are going to modify them in place, right? So uint 32t pointer d. Great. And then we're going to write a test, ChaCha20 test.c, and in here we are going to include CUnit. Well, CUnit, I think it was, what did I actually do? util-h, I think, and include CUnit basic h or something like this. And then int main void return 0. And how do we register tests? Okay, no, I think it's testdb or whatever. CUnit CU test registry. Yeah, I think there is some idiomatic way to do it. So tutorial, can you get a tutorial? I think it was this one that I used initially, right? Okay, basic and CUnit. CUnit H, okay, great. And now CU initialize registry, CU psuite suite. I'm going to move this to the right side and equals CU add suite ChaCha20 suite, and we pass null functions because we don't. I think these operations. Okay, so it's an initialization function and a cleanup function. Okay, and we are going to need some tests. Cleanup and return 0, right, like so. And then we are going to add tests. So also we probably don't need this testdb thing. Void test ChaCha20 QRound. Void and CU add test suite test core QRound function, and we add the let me pass the function pointer to test ChaCha20 QRound. So now if we open the make file, let's see, if we make test, we know that we want to compile CCO test test, what was it? We need to link CUnit, I think, and we want to include ChaCha20. Okay, we want to include ChaCha20.c and ChaCha20 test.c, ChaCha20c, and okay, I'm going to take a quick peek at my older code. What do we have here? I think it was in TOTP. No, not here. Was it in Kernighan and Readshift? TOTP in makefile? Yes, okay, so this was a very idiomatic expression, but this is actually going to help us a lot. So if we say that cc is clang and c flags, ld flags is going to include CUnit, because I think we're going to need it, and then we specify these, then I think if we run make test, okay, we need to touch ChaCha20.c and now make test. Okay, what does test say? Okay, test runs just fine because we didn't really specify any assertions in here. Then CU. Okay, we also need to basic run test, I think. Basic run tests, okay. So now make test and run this test. It's going to pass, and we get a nice representation of our test suite, because basically there is only one test and it doesn't make any assertions. So I'm also going to specify that this should also can I somehow specify like a make file default target or something. A default target or target, or like a target template. Okay, can we somehow, oh, yeah, okay, whatever. I'm just going to run this test thing in here. So make test, and we also want it to be forced. So, and now it's going to fail because, okay, so this means that we actually cannot use this. We have to actually specify ChaCha20.c and ChaCha20 test.c like this. Okay, so now we have like a makefile that will run tests for us, and it will even run these tests for us if we rerun the make command. So I think this is a good point to commit. Also, we want to ignore the test thing. The test binary, right? I think we can also just straight out ignore all exe files. Okay, git add, git commit, set up test suite. Okay, so now in ChaCha20c, we can actually start implementing this ChaCha20 quarter round function. And maybe we can start by running the actual, you know, defining the actual tests, right? So you int a 32t a b c d a equals 0x 11111111, b equals 0x 01020304, c equals 0x 9b8 d6 f43, d equals 0x 01234567, and we need to specify this ChaCha20h. Okay, ChaCha20 quarter round with pointers to A, B, C, and D, like so. And then we can assert CU. How do we assert in C again? Include CUnit assert. Okay, how do we assert things in CUnit again? cu assert equal, where is it defined? Assert equal, we assert that a equals 0xEA 2A to 92F4. cu assert equal that b equals 0xCB 1CF8CE. cu assert equals c, and this is 0x4581472E. cu assert equal d 0x5881C4BB. Okay, so let's run the tests again. And ChaCha CUrun, test ChaCha CUrun. Wait, what? Aren't we compiling them together or what? This is ChaCha20C. Okay, so we're going to have to define this ChaCha20 CUrun function, otherwise it won't compile. But for now we just don't do anything in it. So now all of the assertions have failed because we aren't doing anything in there, right? So we can start by implementing the ChaCha quarter round. So the ChaCha quarter round is basically just operations like this. So I think we can just write plus a equals b. Also I think we may have to mask it in with like 32-bit masks. Otherwise, we may end up with like 64-bit arithmetics. I'm not exactly sure if this is strictly required, but I think this was the way this article did it. So we could, for now, we could probably just ignore it and see if we get any errors. Okay, d equals the what was it, a, and now we have this left rotating function, and this basically means that we take this d thing, we move it 16 bits to the left, and then the bits that are moved out of the picture have to be placed back in there. So this is not an actual operation in C, so we can define it as a macro, or we could define it as an inline function, inline void okay, rotate left with 32 bits, right? So we take a uint 32t number and int offset, and now we can say return n moved by offset summed with n I think this is just enough. 32 minus offset, and then we mask everything with 32 bits. No, we don't. Inline uint 32t. Okay, like so. So let's try. I'm not sure if this is exactly how it should work, but let's try. Equals rot l d moved by 16 bits to the left, and then they just do the same thing for all the others. So c plus equals d, b XOR equals c, b equals rotate to the left b, and we move it 12 bits to the left. Okay, a plus equals b, b XOR equals d XOR equals a, and then d equals rotate to the left d, and we move it 8 bits, and then c plus equals, and make it static here, plus equals d, b XOR equals c, and then b equals rotate left b by 7. Okay, okay, this was that easy. I mean, for now it works. It was that easy. Maybe we even don't have to actually mask these. Yep, so we don't even have to mask anything with we don't even have to do any masking. At least on this machine. I will try it later with on an ARM machine, and we'll see if it still works. Okay, great. So now we have a ChaCha Q round. So it's a good time to commit. Implement and test Q round. Okay, we have the Q round. So the next thing we're going to do is plus denotes integer addition modulo 2 to 32. This is an XOR, and this is a left an n-bit left roll towards the high bits. Yes, so we have this test vector, and the quarter round function works. And just to make sure it's really actually testing something, let's comment out one of the operations and see if it still passes. So now if we comment out one of these operations, then the tests are failing. And now if we add it back, it works again. So it's that easy. And then it says the ChaCha state does not have 4 integer numbers, it has 16. So the quarter round operation works on only 4 of them. Okay, so this is to say that the ChaCha state is actually defined as a 16 integers, right? So I think we can define the ChaCha state. Type def struct, and what was it? What was the terminology for it? The the description of the ChaCha algorithm will at various times refer to the ChaCha state as a vector or as a matrix. This follows the use of those terms in this document basically. The matrix notation is more visually convenient and gives a better notion as to why some rounds are called column rounds, while others are called diagonal rounds. Here's a diagram of how the matrices relate to vectors using the C language convention of 0 being the index origin. The elements in this vector or matrix are 32-bit unsigned integers. Okay. So I think I'm just going to call it elements for now, or maybe words, because it's easier to type. And then this is going to be a 60. Wrong language. And yeah, wrong language, totally wrong language. CUnit32T, and this is ChaCha20. Yeah, I'm just going to call it ChaCha20 for now. So we have this quarter round, and this section defines why we actually need it. So the ChaCha state does not have 4 integer numbers, it has 16. So the quarter round operation works on only 4 of them, hence the name. Each quarter round operates on 4 predetermined numbers in the ChaCha state. We will denote by quarter round x, y, z, w, a quarter round operation on the numbers at indices x, y, z, and w of the ChaCha state when viewed as a vector. For example, if we apply quarter round 1, 5, 9, 13 to a state, this means running the quarter round operation on the elements marked with an asterisk, while leaving the others alone. Note that this run of quarter round is part of what is called a column round. Test vector for the quarter round of the ChaCha state. For a test vector, we will use a ChaCha state that was generated randomly. So this is a ChaCha state. Okay, so we could probably also implement this, and what it means is that I'm going to define it like so. So ChaCha20 Q round is the direct concrete. So I want to implement 2 functions. This one is going to be actually calling the numbers, and another one is going to be another notation implementation of the ChaCha Q round. And ChaCha20 defines the ChaCha20 vector or matrix with 16 32-bit unsigned integers. Okay. Yes, I think we got scrolled to a different place. Okay, so the quarter round. I think we could define the Q round as a macro. Q round state A, B, C, D. And this is basically just going to be ChaCha 20 Q round, and this is going to be a pointer to state at A, state at B, state at C, and state at D, right? So this is like a short form notation, so we don't have to actually write out all of these longer things, so we can just use a shorter notation like this. And in the test, and we can define it like so: static const and static const ChaCha20 20 Q round test vector, and this is an can we define it like this, or can we define it like wait, also this state thing is going to be a pointer. It's probably going to be a pointer to an actual state, so we're probably going to need something like state words. You'll see how I'm plan this to work in a moment. So const ChaCha20 pointer equals, can we do it like this even? Words. Okay, initialization of non-aggregate. Okay, I don't think I can do it like this. Anyway, what does this error message mean? Okay, but it looks like this is only an error in C++. Designator and initializer for scalar type. Okay, so I can actually do it with, as long as I use this, I can do it as long as I use, what was it called? As I use as an actual, not a pointer. And then I probably have to copy this vector and I paste it here. And then I basically have to okay, I'm going to clean it up in Elixir. String equals this. So words equals string split string split on any white space. Great. Also, we have to trim it. Okay, great. And then enum map fn word, we output the word like this. and then we enum join with a we join them with commas like this. Okay, great. So this is the round test vector, and we could probably write it. Okay. Also, I'm going to move this the actual implementation of this text ChaCha20 Q round thing to after main function, and I'm going to move this afterwards as well. So this way we can like write at the end of a file, and then the expected vector should look kind of like this. Initial vector, and this is going to be expected vector, and the only difference is that this third word is going to be this, and then this seventh word is going to be, which one was it? We replaced 2a like this, and then 533 is going to be replaced with this, and then CCC is going to replace this 3D thing, right? And then in the test, we define this another test ChaCha Q round on ChaCha Q round on state, let's call it Q round macro on ChaCha20 state struct. Okay, and now void test, what was it called? Okay, so ChaCha20 state, and I'm going to string copy or like mem copy from, what was the signature again? Mem copy memory area. It copies n bytes from memory area source to memory area destination. Okay, so destination is state words, maybe something like this, and then the source is going to be ChaCha initial vector words, and then what else? Size tn. Oh, and by the way, why is it okay? And this is going to be 16 times size of unit 32t, right? Too few arguments. Okay, why is this okay, mem cpy? Okay, great. Does it compile now? Okay, it does compile, and then Q round state and then it's going to be 2, 7, 8, and 13. Cannot take the address of an R value of type. Okay, does it want this or what? Remember, reference type ChaCha20 is not a pointer. Did you mean to use dot? Wait, what? No, I don't think this is the way we wanted to use it to do. Why does it work? Why does it work? We are. Like seriously, why does it work? It's not supposed to work. We're passing a pointer, right? If we're passing a pointer, okay, this is. I'm going to write the assertions to see if this actually works. I is less than 16, I++, and then CU assert equal state words at I. It has to equal ChaCha current expected vector words at I. And this is not going to work, I think. What? How come does this work? Okay. This just shows I don't really understand how. I totally have no idea why this works. But, you know. So are you trying to tell me oh, okay, so this works because, okay, I don't want to do it like this. I want to do it like this. So this becomes a pointer, and this is going to be actual state. We want it to be the pointer, right? Yeah, so the reason it was working is because it was like explicitly expanded. And now, compatible integer to pointer conversion. So unsigned int. No. No. So now this has to be an actual. Yeah, this could technically be a function, like an inline function call or something. But anyway, so now this is also going to expand correctly, right? Okay. So now segmentation fault. Okay. We're passing this. But why? Is this like null or what? Okay, I think I'm just going to rewrite this QRound thing as a function because this is going to be much easier, right? Void QRound ChaCha20 pointer state int A, int B, int C, int D. And this way we do not need to do it like this. And then in ChaCha20C, a void QRound and ChaCha20 state int A, int B, int C, int D. And by the way, can I shorten it? Yes, I can. So now okay, no, I cannot shorten it. I have to actually specify the int type before each and every one of these. Int D. Okay, great. So now I can say QRound ChaCha20 QRound, and I'm going to pass the pointer to words at A, state words at B, state words at C, and state words at D. And this would probably be inline. Can we use it now? Okay, we are still getting a... Okay, so why are we getting a segmentation fault now? Okay, we are not getting a segmentation fault now, but okay, great. This works. It was kind of confusing. But anyway, we do have a test for our helper method for the QRound. And I think this is a good time to commit. Okay. So now there's the ChaCha block function, and the ChaCha block function is the actual place where the actual magic happens, because it runs like 20 quarter rounds on the... No, it doesn't run 20 quarter rounds. It runs 8 quarter rounds. So, okay, I'm going to read it and then we try to implement it. The ChaCha20 block function. The ChaCha20 block function transforms a ChaCha state by running multiple quarter rounds. The inputs to ChaCha20 are a 256-bit key treated as a concatenation of 8 32-bit little endian integers, a 96-bit nonce treated as a concatenation of 3 32-bit little endian integers, and a 32-bit block count parameter treated as a 32-bit little endian integer. The output is 64 random looking bytes. Okay, so what this means is like these are these little endian integers, and this sounds scary, but this is actually the way most CPUs work these days. So basically, if you just put it in memory, this is how it's going to work. And I mean, I've only tested this on an Intel CPU, but like I could probably just also test it on a Mac, and it should probably still work. And then there is this nonce, and this is what we mentioned, that we cannot, like, this is a nonce, it is a number you cannot reuse. It doesn't really need strong entropy, it just means it cannot be reused, and it's not secret, and you're going to need it to decode, decrypt, and validate an encrypted message. And then there is this block count parameter, which means that this is the because ChaCha20 is a stream cipher, it operates in block mode. In stream, it operates as a stream cipher, and this block count is this block counter is basically a counter you use as an input in the cryptographic function. The output is 64 random looking bytes. And this is also to say that ChaCha is not a block cipher, it is a stream cipher. It generates a key stream that you then apply on the like plain text using XOR, and you get the ciphertext. And then there is poly 1305, which I haven't read the spec yet. I haven't tried to implement it, but it's probably not too complicated either. But there is much more maths going on in poly 1305. Okay, the ChaCha algorithm described here uses a 256-bit key. The original algorithm also specified 128-bit keys and 8 and 12 round variants, but these are out of the scope for this document. In this section, we describe the ChaCha block function. Note also that the original ChaCha had a 64-bit nonce and 64-bit block count. We have modified this here to be more consistent with recommendations in RFC 5116, which is what? Okay, this is some cryptography related RFC. This limits the use of a single key nonce combination to 2 to the power of 32 blocks or 256 gigabytes, but that is enough for most uses. In cases where a single key is used by multiple senders, it's important to make sure that they don't use the same nonces. This can be assured by partitioning the nonce space so that the first 32 bits are unique per sender, while the other 64 bits come from a counter. The ChaCha20 state is initialized as follows. Okay, and by the way, this is it's actually very difficult to keep track of nonces, so most of the time you just use random keys, like random nonces, and you just make sure not to use the nonce more than 2 to the power of 32 times, which is about 4 billion. The ChaCha state is initialized as follows. The first 4 words 0 to 3 are constants. And also these constants, these are not some strange constants, it's just these are the words. The words are initialized with the actual term encrypt. Like there was this yeah, we could just try to decode it, right? So IX, wait, are the tests passing now? Yes, they are. Okay. So the words are, okay, words, we enum split by this, not enum split, string split, right? Okay, and then enum map fn word, and then what was it? We remove the replace word 0x with nothing, and then enum join, and then base the code 16 with case lower. Okay. So these are actually reversed. So we could what was it? Binary bin to list. Okay, and then enum chunk every 4 bytes, and then enum map enum reverse, like this. So now we have reversed those words, and then we enum join. We join them. Can we join? Okay, so these words that come from the specification, they are specified in lower endian order, but that just means that if you just put these 32 if you just put this constant in memory, then you will end up with this. If you just put this word in memory, you will end up with this constant. So we could probably, I think we could just copy this and just use it in the initialization thing. The ChaCha state is initialized as follows. Okay, the first 4 words are constants. The next 8 words are the 8. Okay, we're going to need wait. Oh, we have to run this 10 times. Okay. But do we have like a test vector? Yes, we have. Okay, so we're just going to write a function to do it. So in ChaCha20h, we define a void ChaCha20 setup block, and this is going to take a pointer to a state, and then the key is going to be a uint 8t vector of key, and then a uint 8t vector or of nonce, and a okay, where does the block count belong? It's at the end, right? Okay, it's here. And this is the nonce. Okay, so this also goes here. Okay, uint nonce and and then the block count is okay, but why is nonce? But why does it look like the nonce is actually a big endian or what? Okay, so why does it seem like the this block counter is big endian and the rest is little endian? Like why? Okay, anyway, I'm just going to implement it like this: uint 832 block counter, and the block counter. Okay, so now we can define a test. Void test ChaCha20 setup block void. Okay, void test ChaCha20 setup block, and we add this to the test suite. CU add test suite test setup ChaCha. ChaCha20 setup block, and then the test function is test this one, and this runs. It doesn't have any new assertions, so it passes. So let's see, ChaCha20 state, and then the okay, this is going to be the key. So we copy it. We probably also need to clean it up. So let's say this string split key, split it by this, and then enum map and fn byte 0x byte, and okay, and then we enum.join with a comma. Great. So this is going to be the key. We can say static const test ChaCha20 setup key, and this is a pointer, uint 8t. This is like a vector, and we paste these. Okay, so now the nonce is going to be static const uint 8t test ChaCha20 setup nonce, and this equals to this, and we apply the exact same operations as on this one. So key equals and we do the same. So okay, and then the block count is 1. Okay, so I don't think this is going to work this way, or maybe it is. Oh, you know what? I think it will actually, because this is going to be, this is the word, and once you actually serialize it, it's going to be little endian, so it's going to be the other way around. This is, I remember this was very confusing for me the first time I tried it. Okay. ChaCha saved with the key setup. So now we run the ChaCha20 setup block with the state, pointer to the state, and then the key is going to test ChaCha setup key, and then it tests ChaCha setup nonce, and the block counter is 1. Discards qualifiers. Unsigned char. Okay, yeah, this complains that I'm passing a. Okay, I'm just going to treat this as I'm just going to define this to use const keys, like so. This way it won't complain. And then we have this setup. We have this key setup vector. So we can just define it as the test ChaCha20 setup expected state, and now we have this. We have these words. So once again, stir equals this, and I think we had some operation that actually worked with this, right? No, not this one. So words, okay, yes, like this. This is the expected state, and we just paste it here, and we can say, yeah, we're just going to use the exact same thing, and we assert this state words is this one, and we compare it with ChaCha test ChaCha20 setup expected state. Okay, let us run the tests. Make test. Undefined reference to ChaCha20 setup block. ChaCha20C. And okay, I'm just going to copy the declaration. And okay, what do we have? We can just use memcopy for this, right? Destination is what was the memcopy? Destination like this. Okay, so memcopy state words, and we copy expand 32 byte k and 32 bytes. I think this will work. And then for the, okay, let's see, make test. Okay, so 12 of the assertions are failing, and then we put state words at, this was 12, right? Equals block counter, make this. So now one less is failing, and then the nonce. Okay, so we can write a helper function, static copy little endian word to the yeah, I'm just going to write a helper function to static uint32t get little endian word at address, and this is going to be uint8t pointer vector. Yeah, I'm just going to call it vector. So this basically means that you return what was it, vector at 3, we move it 24 bits to the left, so and we have this vector at 2 which we move 16 bits to the left, with vector at 1 which we move 8 bits to the left, and vector at 0. So for okay, so what we okay, the key goes from here to here, right? So we can say that at a vector at index 4 of the state, we're going to put the key starting from here. So for int I equals 0, I is less than 8, I plus plus, we know that the index of the key is going to be state at words at I equals get little endian word at key, and the index at the key is going to be I plus 4 is going to be key at index of 0 plus I times 4. Okay, can it work like this? Oh no, this is the wrong language. Oh yeah, like this. Oh yeah, so I'm going to pass it as a constant. Okay, let's see if this works. Okay, so now we are down to 3 errors, which means we are correctly copying the key to the state, and then for int equals 0, int I equals 0, I is less than 3 and I plus plus, we do the same with state words I plus 12, no, plus 13 equals get little endian word with nonce of I times 4. Like this. Also, we do not need to cast this key in here. Does it work? Okay, so we are correctly copying this state. We are correctly doing the setup. I don't know if actually passing the string constant in here is the correct approach, but it definitely works. So I guess, Also, this is not 32 bits long, this is 16 bytes long. Okay, yes, good. So now we have this working. I'm going to commit and take a break, and I'll be back in a few minutes. Implement and test ChaCha20 setup block. Okay, great. Wait, why can't I? Okay. Okay, I'm back. I had some difficulties. I had some technical difficulties starting and stopping my stream. So, in the meantime, we have a working implementation of the setup thing. And I think the next part was actually implementing the rounds. So, okay, so the actual round would be, we need to define this this thing, void ChaCha20 okay, ChaCha20 inner block. Oh, yeah, I think we can actually define it as a static function, right? So ChaCha20 block, and so we pass the ChaCha20 state, and then we do it when we're probably going to have to do the actual setup inside of here, key and I'm going to pass the nonce first, because that was what I did in the block setup thing. And you int 32t block counter. I'm just going to call it counter. Okay. So we can probably do it with the TDD way, or we could, you know, ask Claude to write it for us, but we are doing actual vibe driven development, so we are going to write it by hand. So, okay, I'm going to define a test, void test ChaCha20 block of void, and then CUnit suite test ChaCha20 block, and in here void test ChaCha20 block void ChaCha20 state ChaCha20 block, and we pass a pointer to the state. We pass the same key, ChaCha. We pass the same nonce, and we pass the counter value of 1. And then we expect the state to be like this. So words is going to be, okay, stir equals this. We paste it and serialize like this. So, okay, static. Can we do it const actually? Yeah, I think we can do it as a const. right now. Okay, static const ChaCha20 test ChaCha20 block expected state equals words equals this. Okay, and now we can make the assertions. So we compare the states with test ChaCha20 block expected state. Make test. Now it's going to fail because ChaCha20 block is not defined. So we can define ChaCha20 block, and this is going to take ChaCha20 state, and actually we could copy the declaration from here, like so. Why does it say it's a conflict? Okay, because of this. So now if you run the tests, it's going to fail because none of the expected words are actually matching. So what we can do is first we do the ChaCha setup. We pass the state, we pass the key, we pass the nonce, and we pass the counter. And then it's still failing. And afterwards we do 10 rounds. So the round contains an inner block, static void ChaCha20 inner block. And this takes a pointer to the state. And I'm going to put it on the side so we can have like a cheat sheet. So this is basically going to be a bunch of calls to queues round 0, 4, 8, 12. And there are 8 of these, so I'm going to paste it 7 times. Okay, so this is 1, 5, 9, 13, 2, 6, 10, 14, 3, 7, 11, 15, 0, 5, 10, 15, and then 1, 6, 11, 12, 2, 7, 8, 13, and 3, 4, 9, 14, like so. So now this is still, okay, we haven't used it yet. For int I equals 0, I is less than 10, I plus plus. ChaCha20, no, not ChaCha20 setup block, ChaCha20 inner block with state. And now it will still not work because we still need to do that one thing. So we have to add every number okay, so we need to copy the initial state first. So okay, well actually uint 32t initial state 16 mem copy initial state, and this is going to be state words, and this is going to be 16 times size of uint 32t, like so. So we run the inner blocks 10 times, and then we copy these. We add the initial state to the end state. So I plus plus and state words at I plus equals initial state at I. And now, so why does it only work for 8 of these? I am bamboozled. I am totally bamboozled. Wait, maybe like this: state words at I equals state words at I plus initial state at I masked to like a 32-bit integer. Would it help? Nope. Totally no difference. So, okay, we know that the setup block function is working correctly. Did we do something wrong with the inner block? 0, 1, 5, 9, 13, 2, 6, 10, 14, 3, 7, 11, 15, 0, 5, 10, 15, 1, 6, 11, 12, 2, 7, 8, 13, 3, 4, 9, 14. We did the inner block 10 times. Okay, are the words actually the same? Like, are we actually copying it correctly? Copy n bytes of source to destination. Inside in 16, we are copying the words. Okay, what if we did it like this? What if we just copied this by hand? Initial state at I equals state words at I. Nope. Totally no difference. Okay, we know this setup should be correct, right? This setup is correct. Are we actually copying the test vector correctly? You know what? I know why this is, because we have to actually do a setup after. We have to copy these values after we setup. Why? What's wrong with me? Okay. Yeah, sorry for that. So we do the setup after we first set up the block and then copy the values. Great. So now we have this serialized block, and I think this is a good place to stop the video, because then it's only going to be even more complex. Because we are going to have to split the plain text into blocks, and then we have to serialize them with encrypt them with the counter mode, with the stream cipher, and all of this. And this is all very interesting, but I think this may be a bit too long for this video, so I'm going to stop for today. And I hope you learned something. If you enjoyed me yapping about the C programming language, please consider liking and subscribing. I'm going to need your subscriptions to offset the people who are going to unsubscribe after I start making travel videos. And well, I hope you learned something. I hope you enjoyed it. And the name is Karol Moroz.